Welcome everybody to this robotic seminar series sponsored by Lockheed Martin and Maryland Robotics Center. Today we have the great pleasure of having Dr. Maggie Wigness present for us today. She is a researcher in the Computational Information Science Directorate at DEVCOM Army Research Lab, ARL. She earned her PhD in computer science from Colorado State University in 2015. Maggie has led and shaped the research directions in many ARL collaborative alliances as a capital lead for the Robotics Collaborative Technology Alliance, RCTA, a technical integration lead for the Scalable Adaptive Resilience Autonomy, SARA program, and the Collaborative Research Alliance. As a deputy collaborative alliance manager for the Internet Battlefield Things. And Maggie's current research interests are in the cross-section of machine learning, computer vision, and robot autonomy with a specific focus on adaptive and online learning from human demonstration. Today, she's going to be talking about their work in human-centered machine learning for autonomous navigation. Welcome.
Yeah, thanks. So I'm going to go ahead and take off my mask while I present here, if you guys don't mind. But thanks, Yancy, for having me and for the introduction. I won't stay on this slide too long because I think we've pretty much covered sort of the introduction. But yeah, I'll focus on human-centered machine learning and what we're using that for autonomous navigation today. Maybe this doesn't work. Let's go this way. Let me provide a quick introduction to sort of my background. You heard a little bit about that in the intro, but I did get my bachelor's in computer science in 2010 out in Oregon and did my PhD studies at Colorado State University. So when I was there, my emphasis in my PhD work was really focused on computer vision and how we can efficiently collect and label large sets of image data sets. And so strictly focused on computer vision and how we could train models efficiency with limited human interaction. Towards the end of my PhD, I actually came out here to work for Army Research Laboratory and started using the perception models that we were building from my PhD work to do visual navigation. So in this particular video where you can see the perception up in the top right corner, and we're basically just hand coding costs and saying anything that we identify as road, that's like what we want to drive on. And so we started working a little bit on that. I joined ARL after I got my PhD because I really loved working with my colleagues there. And since then, I've worked on a number of different projects. As mentioned, I was a capability lead for the Robotics CTA, and I led the efforts on sort of context-aware navigation, and I'll talk a little bit more about that today. But the idea in that particular image is that when a robot's operating autonomously, there may be different things happening in the environment, and we may want to change the maneuver of the robot based on the context and what it's perceiving in the environment. So if there's an enemy, maybe we want to move a little bit differently. If there's a large crowd of people, how do we adjust navigation in that sense? And I'll talk a little bit more about that. And more recently, today I'm really going to focus on the robotics aspect here. But more recently, I've become the program manager of the Internet of Battlefield Things Collaborative Research Alliance, which is less focused on robotics, but more focused on static sensors and really any asset that can sense the environment. And we're focusing on how to take this large-scale environment, sort of like a mega city, and all the sensors in that environment, and do edge AI and sort of real-time and resilient sensing for applications related to command and control. So a little bit of my background, and let me just, I don't know how many people are familiar with ARL, but just quick background here. So the Army Research Laboratory is the Army's corporate laboratory. We have a lot of sort of research that goes on within the lab. So what I'm going to focus on is very specific, just a small branch of what all of ARL does. But the overall mission is to operationalize science for transformational overmatch. So what does that mean? We're all about taking the science that we're learning, whether that's for robotics or sensing or any other sorts of science there, and actually getting it in the field because our end customer is the soldier. And so the faster that we can get sort of this science out to them, the better overmatch or additional assets that they have to perform their job. So we also serve as Army's primary collaborative interface to universities and industry, which is great. So most of the work I'll talk about today is in collaboration with different universities. So as I mentioned, I'm going to talk a little bit about sort of autonomy and robotics at ARL, and there's a number of different groups that work on autonomy and robotics. But at a very high level, the group that I'm most closely working with is really focused on advancing autonomous maneuver in unstructured or off-road environments, and also looking at different teaming behaviors, so how multiple robots are actually interacting together. And as I mentioned, we do this collaboratively through a number of external programs at ARL. My focus is solely on ground robotics and the application of those. I do not do much with UAS systems, although we do have a large number of researchers that focus on that as well. And then I'll quickly just mention that most of the work that I'm focused on is really based in field experimentation and sort of real-world evaluation. We do some work in simulation, but the point here being that ARL has really invested in a large autonomy architecture or software stack that allows us to execute sort of the basic concepts of robotics for autonomous navigation. And so that includes things like perception and SLAM algorithms and planning and so forth. So everything that I'm going to talk about today is actually embedded in this large software stack that we can run on a number of real-world platforms at different experimentation sites. So I don't know, let's see. I guess some of those the robots on not the far right, but the two next to it are some of the platforms that I've run a lot of this stuff on. So it's sort of an overview of ARL and some of the autonomy architecture and the autonomy work that's happening. What I really want to focus on today is human-centered machine learning. And so most of what I'm going to talk about is focused on that. So let me start with sort of some motivation here. So there's a lot of interesting perspectives on AI today and what that actually means. I think sometimes when talking and working for the Army and talking to Army leaders who are not necessarily up to date with the current state of the art in some of this, when we talk about AI, what this often is referred to as using really large-scale data sets for offline machine learning to do things that we've become pretty good at, right? Perception tasks, so things like semantic segmentation and object detection. And in order to do this, right, what do we need? We need very intensive data collection. So, right, deep learning and computer vision advances really started with ImageNet, which contained millions of images that we could actually learn to identify correctly, and annotation tools like LabelMe and a number of other things that have come about. So in addition to the large sets of data, right, you need massive compute, right, to actually train these networks, and some of that is like starting to drop off, right? We can do things faster now, but in general, this is sort of what people think, or some people think when we talk about what AI is. Lots of data, learn an object detection model, and it requires massive amounts of information. So what's the problem with this? A lot of real-world scenarios, let's say, these sorts of AI applications don't scale, right? So just two examples here. In the top right image, we have some images from the DARPA Robotics Challenge. And the idea here was that, or what this is trying to emphasize is that you see a lot of researchers in the background that are fine-tuning. So they sort of do a run on one of these challenge cases, and then they're back fine-tuning for their next run, right? Because either their parameters were wrong or they didn't have the correct training data or whatever. So very brittle. And the other example here is from RoboCup, right? And similarly, right, you can see researchers like on the field trying to hard code and adjust things for the soccer players so that these robots can actually play soccer. And this is for a number of reasons, but the idea is that these may not scale well when you're just trying to use large sets of data, train offline, and then deploy. So the potential solution, one potential solution, probably not the only one, right, but is to focus on sort of human-centered machine learning. And let me just say that, to go back to the scenarios, that in order to fine-tune those models from before, you needed machine learning experts, right? People who understood what was running on board the robot to actually modify the algorithms or any of the code. So with human-centered machine learning, the idea is to hopefully scale sort of this model generation or learning by allowing a wider variety of people to actually train the systems, and specifically sort of people at the point of need. So this is really just, sort of an illustration of the fact that we're not talking about machine learning experts. For us, our use case at ARL is focusing on the soldiers. So, soldiers who have no idea what machine learning is, how can we allow them to train systems or adapt systems? But you could see sort of just a number of people training for different sorts of things. So what is human-centered machine learning? Kind of described it, but sort of a formal definition here for everybody. It's really just the concept of incorporating those end users into the training process. And the end users are the people who are actually going to be using the systems, right? Not people who are just training the systems, but who the customer is, actually. And to actually build this intelligence or develop the models through this sort of human feedback or human interaction. And it's very small scale human interaction. So we're not talking about trying to hand code something that's very complex. So what are some examples of natural interactions? It could be sort of evaluative feedback or rankings. So, scores out of 1 to 10 or good or bad and whatnot. For a lot of what I'll talk about in terms of navigation, it's really just about using a remote control to drive the robot around and sort of providing demonstrations. But the idea is that these interactions should be relatively simple. They should be pretty natural to a human, any human. And this would ideally be used for continuous improvement, so they can continually provide this to adapt whatever needs to be adjusted. So as an example, and what I'll talk about for the rest of the talk today, is how ARL, and this is mostly going to focus on the work that I'm involved with. We have a number of other research efforts at ARL focused on this, how we're using human-centered machine learning or human demonstration to build more robust autonomous navigation systems. So again, you have sort of a human teacher. It's using an Xbox remote to provide some sort of information, and then sort of that underlying intelligence is built and then put on a robot for some sort of application. So I'm going to provide a number of examples on how we've used human-centered machine learning and really focusing on 2 tasks. So again, this is a navigation task, and at the very basic level, the navigation task is just to traverse between point A and point B in an environment. Okay, so that's sort of the whole goal. And we've used learning from human demonstration in 2 contexts, one for global planning, where the idea is not really about, it's sort of to identify higher level behaviors, or behaviors that are more context aware, terrain aware, mission aware. So really high level behaviors, and I'll talk about some of those. In that particular example, it could be about, maneuvering around surveillance cameras, for example. And then we've also used human-centered machine learning for local planning and control. This is more focused on terrain-aware adaptive behaviors. So this is really about learning control parameters, velocities and torques and things like that to actually maneuver the robot within an environment that has very unstructured terrain. So again, the context of what we're looking at is mostly on operation in unstructured or off-road terrains. So I'll talk about both of these cases here throughout the talk. So I'll first talk about the high-level global planning scenario to start. So as I mentioned before, the goal here is to identify high-level behaviors. And I don't know the background of everybody here, but really what we're ultimately trying to do is generate a cost map that a global planner can use to then plan paths within the environment. So what we're actually producing here is a cost map. And we're going to do this by learning some sort of reward function that encodes the behavior based on the features within the environment. So environment features or environment context is going to come from the sensors that are on board the robot. And so this will be from visual perception. It could actually be other features that we define that aren't, that we can't physically see, and I'll talk a little bit about that. So this relates more to like mission information, areas that are dangerous, maybe we want to avoid. And the goal here is to be able to use human demonstration to adapt these behaviors very quickly when an environment changes or if a mission changes. So again, this example is focused on sort of maybe our baseline autonomy. If you can see the robot up there and sort of the star of where it's trying to get to. The baseline autonomy may just take the shortest path. It won't consider the terrain. It won't consider any other information in the environment. But by developing these reward functions that exhibit specific behaviors, we can pile that on top of what is using for planning, and then we can actually plan paths that maybe take longer to get to the destination point, but match sort of the mission requirements or safety requirements that need to happen. So here's the sort of the learning approach overview. We're using inverse reinforcement learning or inverse optimal control. We see these used interchangeably in the literature, although inverse reinforcement learning is probably more common at the moment. But the idea here is that the human is just going to demonstrate an optimal trajectory by simply driving the robot with an Xbox controller. So what we have as one part of the input is an example trajectory. This is an optimal trajectory in the sense that it depicts whatever behavior we're trying to teach the robot to do. So one of the underlying examples we'll use is if we want the robot to follow the edge of the road. Don't drive down the middle, avoid grass, avoid buildings, and so forth. So maybe a human can provide that demonstration. As I mentioned, that trajectory is going to follow with the features in the environment. And we're actually going to sort of encode a reward function that's in the human's head, right? So they don't understand how to define a reward function or assign weights to the features that it's actually being learned. But we can simply provide a demonstration, and they understand what that means. We all know what that might look like. And so that sort of gets at, like, why are we using human demonstration, right? So if our end users are people who are not machine learning experts, trying to ask them to hand code this information, it could be very complex. Also, when behaviors become much more complex, if we're trying to interweave multiple behaviors, so maybe we need to drive on the edge of the road unless we see something that's dangerous, or if we see something else in the environment, and trying to encode that, even for a machine learning expert, can be very difficult. So as input here, you can see that we have example trajectories. Those form the human demonstration part of what I've been talking about. And then the other set of input are the environment features. And so again, this is could be defined however you'd like for whatever's like necessary to actually depict the behavior. What we're using, again, is output from computer vision algorithms, specifically semantic segmentation. So you can see sort of we have an image that's coming from the sensor on the robot, and each color represents a different semantic concept. So we have buildings, we have different terrains, concrete, gravel, etc. We can take every image that we're actually semantically segmenting and project that down into, and basically create maps or feature maps for every environment feature. We can also use LiDAR sensors to identify obstacles, and so we can generate feature maps from obstacles and so forth. So the feature definition is sort of up to the specific application. This is pretty typical for a lot of learning problems. But we can take both of these inputs and we send them into the training algorithm, and the whole goal, again, is to learn a set of weights that will then define the reward function. And so each of these weights defines sort of the importance or the degree to which the robot should be traversing over these specific features in the environment to actually encode that behavior. So let me provide a few more details here for inverse reinforcement learning. So for people that are maybe more familiar with reinforcement learning, similar problem, except we don't have the reward. So arguably, one of the hardest things about performing reinforcement learning is reward function design. And so if that's difficult to actually do, the use of inverse reinforcement learning is specifically designed to identify that reward function or recover that reward function. So similar setup in terms of like modeling this as a Markov decision process where we have states and actions. within the environment. We have state features, which I talked about. Those are the sort of the visual perception features that we're using. And then again, for this particular problem, we have these optimal demonstrations that we're doing. So that's sort of given. And then the goal then is to recover that reward function. So in this case, we're actually using just a simple linear reward function, right? So we have the set of features, feature vectors for every state, and then our learned reward parameters. And so that will actually give us the reward for every state in the environment, and then certainly the reward for a trajectory, which is the sum of all rewards across all the states. So a few more details on state features and actually the sort of the weights that we're learning the rewards across. Again, this is what we're using for this is specifically focused on a lot of perception information. So you can see that we have, again, camera images and visual features. You can see some of the classes that we're actually detecting. And so this information is what we're learning the reward function across. I also mentioned that we have the ability to define other features that maybe are not visible. So we can take intel about maybe where a surveillance camera has viewpoints, and we can define feature maps across that. Maybe those are areas that we actually want to avoid in the environment. We could have communication radius that's important, and so maybe the robot needs to operate within the communication range, so you can encode features like that. So it's all, again, all dependent on the particular application. And then certainly you can take sort of what we call like the raw feature maps, which are down in that, the black and white images in the left-hand corner that we're getting from the perception, and then do some sort of manipulation on that. So in this case, on the right-hand side, you can see we're like basically producing a Gaussian blur of these features. And this allows us to represent sort of the edges between these different features, which will allow us to get more complex behaviors. So again, here's sort of the combination of what the input is looking like. So in this image here, it's a set of different feature maps, which you can see in the bottom right-hand corner individually, but in the visual map, they're sort of piled on top of each other. So the pink area represents the road, the green is representing the grass, and then we have all other obstacles that's coming from our LiDAR sensor. And then in the red line there, you can actually see a demonstrated trajectory. So in this case, the whole point was to drive on the edge of the road. And so you can see a human has driven the robot, and you can see that the trajectory is pretty close to the edge of that grass and that pink side there. So this is, again, the example demonstration. So how are we doing this? And I won't go into a lot of details here because I have sort of a lot of results and other things I'd like to share. But again, the idea is that we're learning a linear reward function, and we're actually using the principle of maximum entropy. This is a very commonly used formulation for inverse reinforcement learning. The idea here is that any trajectory that has total higher reward should be exponentially more likely to be chosen. And to solve this problem, all we're really doing is maximizing the log likelihood of the demonstrations. So in order to do this, we can solve this with gradient-based optimization. And I would refer you to the original paper on the principle of maximum entropy for inverse reinforcement learning by Siebert. And the gradient here is looking at the differences between the state features that the demonstration travels through. So how often is it traveling on road? How often is it traveling on grass, and so forth, versus what your current reward function would produce when used to generate a trajectory. So here's actually a few more details on that. And so you can refer to this at your own time. But like I said, gradient-based optimization, we can compute a gradient, and that's the most important thing to solve this problem. So what does this look like in practice? As I mentioned, sort of an underlying behavior that we've used as sort of an example is to traverse near the edge of the road. And we use this as an example to showcase that we're not learning a single cost or reward for a specific terrain. So we're not saying that all road is equally likely to be traversed, right? So the emphasis here is on that. And this is an example of some training outputs that we used, or that we got from running maxent IRL on data. And I think that the cool thing about this particular approach is that we were able to sort of train something like this with like 4 demonstrations on the orders of like, you know, the length of this room, for example. So we can actually learn this with pretty low data and actually get a nice reward function. And then that blue outline is just showing there's sort of a little bump there near the edge of the road, which means it has higher reward than the rest of the road there. So how are we using this? I've already sort of shown the top part with the training up on top. So once we have learned that reward function, again, this is all done offline so far, right? So we can learn a reward function. So when we deploy that within the field, we're actually leveraging that reward function, still doing online perception. Then we can, you know, take their environment features, basically doing a dot product with that reward function to generate a cost map, which is then passed to a global planner, right? So now we know where the goal is. We have some cost maps associated with the environment, and then we can actually run this online. So here's not a short video, but kind of a short video on sort of how we're actually evaluating this in the field. And you can see the different sensor input. Again, this is all run live online. And what you see right now in the bottom right-hand corner is an actual demonstration from a human to drive on the edge of the road. And so that particular information is being used in addition to the sort of perception information and to learn a reward function. And then what you're seeing next is the actual controller using this particular reward function. So you can see that the robot is trying to stay near the edge of the road. It's doing a little bit of this. This is a couple years old, and we've fixed some of these sort of S-ing around issues. But you can see that the robot's trying to maintain pretty good distance near the edge of that road there, which shows that, you know, the reward function is good. We're using it pretty well. And I think just briefly here, after it gets to its destination, you'll see sort of our baseline planar, which again is not using any visual information at all. So you can see that it's sort of all over the road. It's driving in the middle of the road, and about halfway to its waypoint, it's actually going to deviate into the grass, which is not a safety concern in this particular scenario. But if the behavior were to be something that really needs to match the optimal trajectory, you know, this would be a bad case. So the other pictures in here just showcasing that we do a lot of field experimentation, and we've run sort of this same model across multiple locations within an environment, and we can do pretty extensive evaluation on how closely the trajectory learned from the demonstrated examples matches the actual ground truth demonstration. And we can use things like the modified Hausdorff distance to compare those trajectories and show that we're actually depicting the behavior better than a baseline model.
Have you done any testing on road sections that are different from where you trained it?
This was definitely trained in a different environment. So the reward model was trained at my lab site in Maryland, and this is actually in North Carolina. At a mount site. So, and we've tested this at other locations as well. So because we're using high-level semantics, if the perception system is still able to identify road and grass and those things, then the reward function works pretty well. So there's a question of when your perception starts to break down, then what do you do? And so let me get to that here in just a second. So those some initial results. And then I'll just briefly go through this. What I mentioned, there's sort of some work that we've used to actually transition between different learned behaviors, right? So we can learn one and deploy that, but what if we're in an environment or mission that where we need to adjust? And so this is part of the robotics CTA. This was actually one of our capstone demonstrations where we took learned models for different scenarios and showed that we could transition between them. So some of the examples were driving near the edge of the road was sort of like a normal behavior. We had a social navigation or socially compliant navigation algorithm that we would deploy if we detected large numbers of humans, and then a covert behavior if the robot encountered some sort of danger, which in this case was a rifle. They're all fake rifles, but Army context here. So here's just a few examples here. So on the left-hand side, you could see sort of that initial trajectory of like driving down the middle of the road. You don't see a trajectory now because those red boxes represent humans. So we've transitioned into socially compliant navigation, and now you can see we've identified a weapon, and that lime green line is quickly deviating to a building to represent a covert behavior. So this is just an example of how we're using the perception that's running on board the robot to identify when the context changes and when we should transition between behaviors. And then on the right-hand side, that video was focusing on how we can actually trigger these behaviors using natural language as well. So another part of the robotics CTA was on sort of natural language understanding. And so the robot was operating, you could sort of see, I think in that blue line was the original trajectory it was going to take. And then the human said, can you go covertly? And so then we could transition into a covert behavior. And then you can see the lime green line is different. And so we have different trajectories. So just a few examples of how we have taken these learned behaviors and transitioned between them either via natural language or perception cues. Now, let me go into quickly on, so the original work that I showed is from several years ago. It's sort of where we're moving is to support online intervention.
Before you transition, can I just ask a question?
Yeah.
So I'm imagining like if each, let's imagine we have like a large fleet of these vehicles out, with different soldier groups. So maybe, the soldiers conducted training and they give some kind of meaningful label to that training, like go covertly or go into the forest or whatever, right? So now you have these reward functions trained across a number of different, soldier groups, maybe consolidated like on the cloud. Now, assuming all the robot platforms are the same, could you then endow each of the platforms with those reward functions that were trained, across the larger network of soldiers?
Yeah, absolutely. Transitioning between, because these are sort of just high-level costs, right? They're not local control, which for different platforms could change dramatically. So those may not adapt as nicely. But for something like this, where a reward function that's based on high-level semantics, we could definitely deploy this on something else. Now, combining, there's a question sort of, and this sort of gets at where I'm going, there's a question of whether or not, if you have multiple sort of groups training these different behaviors, can you combine those? I don't know. We haven't done any of that. What does that mean? And so there's sort of a question, or I guess maybe a feature of human-centered machine learning that you're actually able to tailor to the specific end user. So one commander, for example, may choose or may be more into some particular behavior, whereas another commander maybe, no, I want to do it this way, and this is how we should actually move in formation or something. And so the idea is that you can actually tailor the behavior to the specific end user. So combining from different users, like across a crowd, is something we haven't looked at. We've been more focused on how do you just tailor to one specific person. And let me just move on to the next slides, because I think this will get at some of where we're going as well. But there's this idea of sort of leveraging this entire pipeline in an online fashion, right? So before we collected all the data offline, train a reward function, then deploy it. But what if something breaks down? What if the mission changes? What if the environment changes? What if the mission is different? Now we need to move in a different direction. So we're modifying this pipeline and actually already have and are collecting a lot of data currently on sort of intervention instead of demonstration. So if the human notices that something has degraded or is not happy with the way that the autonomy is performing, then they can simply request control right away. They can take the remote control, push a button and say, you're not operating autonomously anymore. I'm going to intervene and I'm going to show you how to do this or to update your stuff. So we can actually request control, gather that data online, and then run the training online. So right now we're collecting the data. The robot pauses for like 30 seconds, and we sort of update the model that's being learned, and then we deploy that new reward function. So there's, I think there's a number of interesting questions that we're looking at in terms of like, how do we, because a lot of these scenarios we're assuming that the user may be remote from the robot. So it's only using the robot sensors to actually identify when the behavior has degraded. So what sort of information can we display to the user to help them improve demonstrations or identify when a robot needs additional information? How do we sort of leverage that information as quickly as possible to update reward functions in a short time window? Right, so ideally we'd have no interruptions to the autonomy at all. So some of that's processing speed and just sort of hardware constraints, and how do you just sort of optimize that? But there's also questions of like, what if we get a demonstration that's not good? Right, we were running a human study right now, and I've had a lot of people drive the robot and then say things like, oops, like I didn't mean to do that. So how can you automatically infer that that's not the part of the demonstration that's most important? And then sort of throw that out to improve the training speed. And again, things like that just really focused on optimizing how fast we can do this. But this sort of, let me go to the next slide, because I think this kind of ties back into the original question. So one of the potential capability enablers, right, this is sort of like big army thoughts here, is that if we can actually run this online, if we can actually deploy human-centered machine learning, then we're actually providing a forward deployment of the operational autonomy training pipeline, which means that we can do the retraining at the edge. We don't need data center. We don't need to transfer data to a big cloud. We can do all of the retraining on board the robot. And we can do this interactively, and we can tailor this to whoever's using the specific robot. So if they have different perceptions on how the robot should be moving, they can adjust specifically just to them. So maybe that, hopefully that kind of gets at part of your question there.
So one question, this is really exciting that you're changing the reward function.
Mm-hmm.
Typically, we all use reward function in training. That takes a long time.
Yeah.
So can you do, like, I think I heard you saying 30 seconds or pretty quick. Is that the kind of budget you have in mind for the retraining?
I mean, ideally it would be that fast, yeah, like seconds or minutes. And I think this works pretty well for small adaptations, right? So let's just say something slightly degraded in the reward function, right? And you could collect one training example or whatnot, and so you may not need that much time. Now there's questions about sort of hyperparameter optimization. If you have the right hyperparameters, then you can converge to the solution more quickly. So there's lots of underlying research questions on how to attempt this, but ideally, yeah, we could do this quickly online in the matter of seconds to minutes, ideally. There's scenarios thinking sort of like after action reviews, right? So something's already taken place, we have all the data, we can collect that. There's scenarios where maybe we have more time to actually do the retraining. And so in that case, you can take more time. So it's sort of specific to the application and what we're going at. But if we can do it online, that's sort of ideal. So let me quickly get through this last little bit on the global planning. So we've also extended this a little bit to consider uncertainty in the demonstration. So this gets at the fact that either, one, that the human may not actually provide the best demonstration. There could be noise in that. There could be some sort of error. It also starts to get at the fact that maybe we actually hit some sort of distributional shift from the training environment to the operational environment. So new features are introduced or whatnot. So the idea here, and maybe the pictures on the bottom depict this pretty well. We have some sort of environment, very toy environment here, where we have features of interest, things like grass, dirt, forgot the other one, road and water. But in the training environment, we actually don't have any water. And this is a real problem that we deal with all the time, right? We could try to guess what our operational environment is going to look like, but when we show up, it could look different. And so we can collect as much data within the training environment as possible. And so in this case, examples of driving on the road, if that's what we want to do. But if we hit the testing environment that actually has water, and so you can see in the middle there that it's got that blue feature there, which is water, the reward function actually has no idea what to do with that if you're using the original formulation of maximum entry IRL, because we don't have any demonstrations that talk about what to do with that. So the idea with this sort of extension was to actually incorporate some Bayesian analysis to to incorporate that uncertainty to the fact that we didn't actually see that information in the training environment, and then assign more appropriate rewards that could help us be risk averse, for example. And so I think in the right-hand side, it's just showing that if the sort of original model was trained with examples to drive on the road, the red line goes through the road, but it actually goes through the water as well because it doesn't have any information about water. But with the approach that we've put together, it will actually deviate around the water to avoid this uncertainty. And so just like very quickly, again, the idea is still the same. It's still based in maximum entropy inverse reinforcement learning, but now we're just doing some Bayesian analysis, producing a Bayesian posterior from the evidence or from that human demonstration to then to build these distributions that we can use and then compute entropy across those to actually define the reward function. And I don't have a lot of time to go into the details of this. It's a brand new paper, though, that was just published. But the idea here, and this was all done in simulation because it was during COVID. We didn't have a lot of access to robots here. The idea, again, is that we're able to basically avoid uncertain terrain. And so in this case, it's sort of the brown terrain there that actually wasn't seen during the train environment. So we're basically deviating around to take a longer route, but it's along terrain that we're familiar with and that we know is not dangerous. So this is sort of a toy example, but an initial start to what we're doing. And we've actually put this on a robot as well and have some new results on hardware. So I want to sort of shift to local control before we lose all time here. But sort of as we wrap up, sort of for global planning, things like that, if there's any questions, I can answer those quickly.
Yeah, I was going to ask about, so my son has his learner's permit, and I'm trying to map what you're describing to how someone actually learns how to drive. There definitely is a demonstration component. I mean, he's been sitting in the passenger seat for his whole life, right? But there's also, you know, me coaching him when he's behind the wheel. Like, wait, slow down, watch out for that parked car. You got a red light, you know, this kind of verbal coaching. And, you know, I don't think I've ever switched back to the driver's seat to, like, re-demonstrate. Maybe I would for, like, some kind of three-point turn or some parallel parking maybe, but so how am I to understand, you know, the difference between how humans actually learn and what you're proposing here? And is there a way to augment the reward function with feedback from the human during that testing phase?
Yeah, so I actually think that what you described is learning from demonstration, but it's a sort of evaluative feedback. So it's just a different type of feedback. So you're saying slow down, go faster, but you're not physically defining the amount of pressure that you're doing to slow down or speed up, right? So it's a different type of feedback. And I think, let me see if I can let me scroll through here real quick because I think this sort of plays into what you're saying. There's actually what we call the cycle of learning. This was actually not work that I produced, but it is coming out of ARL. And the idea is that there's different types of feedback. So what I'm focusing on is learning from demonstration. I started to talk a little bit about learning from intervention, where you're sort of intervening online and doing sort of corrective. But there's also evaluation, which again is sort of like could be binary feedback or slow down, speed up. And then also reinforcement learning. So there's another aspect there. And so the idea actually is that most of the literature right now is focusing on one specific piece of this learning process. But what we're advocating for is this entire cycle, that we actually need to incorporate all of this information that actually feeds into a system that can be modified. So while I think demonstration is good for some applications, there's certainly other feedback that we can get. And I think that maybe the evaluative feedback ties in a little bit more into how humans learn. And some of that certainly is from demonstration. People watch and they pick up on things, but providing that feedback. Does that kind of answer your question? Yeah. So, and some of the research that I did last summer with a student was focusing on, combining demonstration and intervention together and how to make use of that. So it's starting to get at this idea of cycle of learning. All right, let me jump back up in here. So let me shift to local control, and if there's any other questions on global, we can go back to that. But just briefly, let me talk about how we're using human-centered machine learning for local control. So this is not based on high-level semantics. It's not behaviors. These are really low-level commands that are being given to the robot, things like velocity and torque and whatnot, to actually navigate within an environment. So the challenge here with local control, especially in off-road environments, is that sometimes the parameters that we're issuing to the robot don't get us anywhere, right? We have varying degrees of terrain. We have mixed terrain, so it's not really just, well, I'll show examples of that, but it's not really, can't just often classify as grass or rocks. You have varying degrees of slope, and so the thing is that when we start to use one set of parameters for things or for local control, it may not be the best for every type of terrain in the environment. And so the idea behind some of this work is to leverage human demonstration across a variety of terrains, whether those are individual terrains or sort of these mixed terrains, like in a forest environment where you have grass and dirt and things all together, and then take that human demonstration feedback and actually learn models to issue local control commands. So the idea behind this, though, is that it's terrain adaptive. So we can adjust this based on what we're seeing in the environment. So again, this also has a vision component, and won't go into all the details here. But the idea here is that we're actually doing behavior cloning, right? So we have, if anybody's familiar with that, right? But we have the demonstrations here now, and where it's different. We're not learning a reward function, but we're just trying to output the same command features or clone that behavior that was seen during the particular demonstration. So in this work, again, we're still, well, there's a couple versions of this, so let me walk through it here. The idea is that we can extract multimodal features from the environment, and in this case, we're actually not using semantic perception. And these high-level semantics, we're actually using low-level features like hog and sift and gist features and color features, so very low-level that don't describe any one particular terrain, but just the characteristics of the terrain. So we have these sort of as features, and then we have our demonstrations, and we know which class of terrain that these demonstrations were taken across. So we have specific demonstrations across grass, and the controls used to get across grass, and gravel, and rocks, and things like that. And so part of this learning is actually learning the terrain representations on the left-hand side. So we're learning basically a weight matrix that will take the input features and try to classify the specific terrain. And then once we have learned that, we're also learning another weight matrix that actually is doing the apprenticeship learning. So it's actually delivering the maneuver controls. So how do we classify the terrain and then use that information to then deliver the actual controls to the robot? With the idea being that different types of terrain will require different control commands in order to smoothly navigate across that. And let me have some results here in a second, but sort of the extension of some of this work is focusing on consistent navigation, where the idea is that the commands that are often issued to the robot are not carried out because of these setbacks, whether that's wheel slip or just variation in the terrain that causes us to not actually navigate that. So as a very concrete example, we could tell the robot to go 1 meter per second, but it may only be going, 0.75 meters per second, for example. This has implications on localization, right? So it can mess up our localization algorithm if we think we're moving faster than we are. It has implications on meeting phase deadlines and getting to a certain rendezvous point at a certain time. And so the idea with this particular work, which is an extension of what I just talked about, so it's using the same sort of underlying features to pull out, but the idea here is that we're actually now learning offsets to compensate for this sort of inconsistency. So where the previous work was sort of just focused on mimicking behaviors and producing commands that were similar to what the demonstrator provided originally, This work also is doing that, but learns another weight matrix to actually compensate for any offsets. So if there is wheel slip, how can we identify that that's happening and then actually modify the command even more to get the robot to move correctly. So let me show a quick example here. This is some real-world experimentation. There's snow, so obviously wasn't done out here. This was joint work that we did with Colorado School of Mines with another ARL program. Let me play it again. You can see on the sort of the left-hand side, our baseline local controller is getting stuck on this steep slope, and this has implications because of the snow and what that's done to the terrain. And then with the sort of learned set of weight matrices for our particular characteristics, on the right-hand side, you can see that we're actually able to get up this slope differently. And again, that's because the controls that are being produced are adapting based on whether or not the robot is actually executing these commands correctly. And so I guess down in the right-hand corner, just examples of how we can do very, very controlled experimentation and watch how the controls are adapting across different terrains. So we can have the robot driving across grass and then meet a really nice line into a new terrain, and so we can see how the controls are adapting there. But also go into more complex environments where the terrain, it doesn't really represent one specific semantic. It's not grass, it's not road. It's just sort of like forested area. Like, what does that mean? And so things that we're looking at when we sort of quantify the importance of this, things like failure rate. So how often is the robot actually executing the task to get from point A to point B? The traversal time. So what we find is that when you have more consistent control and adaptive control, you actually have faster traversal time because you have less wheel slip. And then also looking at metrics that focus on inconsistency. So how, again, is the robot actually doing what you're asking it to do? What was the other point I was going to make about that? And then there's some additional work here, interesting questions about sort of the complexity of terrain. So how do you actually quantify that? Nobody really has a good way to do that. And so there's some underlying research on how to identify the complexity. And then once you understand the complexity of the terrain, can you adapt your control that way? So that's really, I guess, my last slide here. It's kind of an abrupt end, but sort of an overview of what we're doing for, like I said, human-centered machine learning for global planning and also local control. So I think there's maybe a few minutes if people have questions. Happy to take those. Thanks.
Thank you so much. So we have a few questions online. Maybe I'll go with those first, and then we can take a few questions from the audience. So,
sure.
Because they were asked some time ago. And this one is from Juman Hossain from UMBC, actually. And I guess this is regarding the first demonstration with the robots. How can it detect edges from an unknown road?
How can you detect what?
Edges from an unknown road.
Edges from an unknown road. Let me. So basically, within the perception algorithm, I think we're sort of getting at something like. Let's see if I can find a picture. I mean, I guess maybe this is a good example, right? This is not a clear edge, but the underlying perception algorithm here is what's really detecting that. So this is using a deep neural network that has lots of training data. Within that training data, we have edges defined. And really, in this case, it's kind of easy to look at the difference between the grass, just using the color, for example, to identify this. So I would imagine that that's a large part into what we're doing there. But that's sort of, hopefully that kind of gets at the question there. A lot of what we do for navigation is actually off-road, so that's what makes it difficult, is actually differentiating between different boundaries of different semantic classes. And I think that's one of the more challenging aspects of navigation in off-road environments compared to maybe the commercial autonomous driving sector, where you have lane markers that clearly define where you're supposed to be going.
We have a couple questions from John Barras, who he will be talking to in a little while. So I'll just read them as they are. Some of your runs clearly show non-robustness. This may be due to learning or to the models used. Have you investigated robustness? And I guess on a related question, I believe the latter has a lot of advantages. It was later in the talk. That is constraint-based, robust, and risk-sensitive IRL, or experimented with fewer samples and new environments by construction. Comments?
Yeah, I mean, a good point about robustness, right? So what we've shown are some pretty basic examples. I think part of what we're getting at with the online adaptation and sort of running this online would help get at robustness, right? In the sense that if things need to be fine-tuned, we could quickly collect that. And again, this could be because we've changed environments, and so we need to adapt in that sense. Happy to talk about this a lot more with John later this afternoon, though.
Questions from that? There was one on...
Yeah, go ahead.
So my question is about robustness as well. So for instance, you showed in the in one of the demonstrations that the car weaves off of the road and goes in the grass, right?
Mm-hmm.
So do you have a local planner that has collision avoidance guarantees such that it doesn't do that? Because if it was water, it's in the grass, and if it goes in the water, that's your robot is gone, right?
Right.
So are there any local planning collision avoidance guarantees in your approach or no?
Yeah, so good point. So clearly within the autonomy stack, there's a lot of different components, right? And so what I talked about is a cost map generation for global planning. So we'll generate a high-level plan of where the robot should go, but the local planner always takes control and defines, tries to approximate that path based on other local constraints. So if there are obstacles, then the local controller should avoid those. We haven't combined sort of the local control that I talked about with the global planning here. So it's using different local controllers, things like MPPI, for example. And so in that case, right, it should avoid some of that. So there are a lot of layers to the autonomy stack, which also makes it hard to evaluate, to know if something is deviating and doesn't look as good, is that because of the local controller or not because of the cost map? So there's good questions related to that. There's also, should say, even at the global planning level, what the cost map that I'm generating is just a layer. There's also an obstacle layer, and those are fused, where obstacle avoidance will take precedence over any of the reward functions that are learned. Now, obstacle avoidance should be learned to an extent within the cost map and reward function that we're learning, because we do use the obstacle map during the learning, but there are definitely other layers that could supersede what we're actually producing. So safety, clearly, and obstacle avoidance is very important, and we do consider that.
And I have a related question to that. So all the demonstrations you've shown so far are in static environments that there's no other moving obstacles, right?
Yeah.
So how is it in a dynamic environment?
Yeah, very good question. And you're absolutely right. These behaviors are all based on static information. We would probably rely on the local planner and the local control to help with some of those static cases. The work that I briefly mentioned about socially compliant navigation was designed specifically for crowded areas with a lot of dynamic obstacles. That's a completely different training algorithm and training approach. But so while I didn't specifically focus on dynamics, there are other, certainly socially compliant navigation and stuff has done a lot of work in dynamic obstacle detection and avoidance and maneuver. Yeah. But good question.
Other questions?
Last one. What about adversaries? Can there be adversaries in such environment that are trying to thwart your plan and trying to throw you off the track? So in Army cases, there must be some that are trying to throw you off the plan. So how do we tackle such a problem? Yeah,
absolutely. I think there's a whole area of research that has to be looked at in terms of sort of the adversarial manipulation and whatnot. There's a lot of, so can't tackle everything, but a lot of research that we are looking at adversarial deception. So we could look at manipulation of images that cause incorrect classification. There's a lot of research being done on that. Again, hasn't been incorporated here, but certainly something that we're really interested in. You're right. For Army applications, this is critical. And so I can't get into the details here. We just don't have time, but there certainly is a lot of work being done in that area. Yeah.
Well, if there's no more questions, let's thank the speaker one more time.
Thanks.